Hey there, welcome back to Math with Patrick. It's June 11th, and we're solving problem number 162 from the Daily Epsilon calendar. Let's show why this kind of large number, 265,837, why it has 11 proper divisors. Just a little bit of vocab before we get into a proper divisor is a number that divides another evenly. So 4 is a proper divisor of 12, and the proper part just means that we're not going to include the number itself. Like 12 is a divisor of 12, but maybe in some cases it's a little silly to say that something divides itself. That's kind of obvious. And so when we're talking about proper divisors, we're just saying numbers that are definitely smaller than another one that do divide it in a whole number of parts. So that's really all we're trying to do today. We're trying to take 265,837 and we're going to try to divide it by whatever we can until we find some proper divisors. And I don't really have a better strategy than walking through the primes and trying them out. I do have some like divisibility tricks though, so let's see if any work. The first one for twos is pretty obvious. We just kind of look for if the number is even or not. Since 7 is odd, the number itself is odd, and therefore it doesn't work. 2 is not a divisor. For threes, there is a kind of fun trick, perhaps, where if you sum the digits and you get a number that could be divided by 3, then your original one also is. And sometimes it saves time to figure out whether or not dividing by 3 is even a worthy task. So that's what I'm going to do real quick. I'll add up the digits. So like 2 and 6 make an 8. 8 and 8 make a 16. These make a 10. And then finally, plus the 5 gives me a 31. And 30 is divisible by 3, so 31 isn't. And so that shows me that this number is not divisible by 3. And so we keep going. 4 isn't prime, so I don't need to check it. Knowing that this is not divisible by 2 is enough to know it's not divisible by 4. With 5s, you can check the last digit. Since it's not a 0 nor a 5, we can skip over 5s and try the next one. And there are some kind of neat tricks for 7, although I really forget them, honestly. So for 7s, I just figure we could do normal long division and see if it works out. So let's try out the long division. I'll ask how many times does 7 go into 2? It doesn't, so I'll put a 0 here. And the next thing to ask is how many times does 7 go into 26? And if you count by your 7s, you'll reach 21, and then 28, and 28 is too big. So a 3 times 7 is the perfect number to put right there. And just as a little side note, when we're doing this long division process, instead of like asking how many times does 7 go into 26, technically we're asking how many times does 70,000 go into 260,000? But just maybe thinking of these large numbers with all these zeros could be kind of confusing. And so the long division process is nice because it kind of pares down these big numbers into smaller ones that are more easy to handle. So I could ask the question, how many times does 70,000 go into 260,000? And that's the same thing as asking how many times does 7 go into 26? And that's a bit easier to think about. So anyways, I'll just kind of fly through the long division process right now. And ultimately, I'm trying to figure out if this number is even divisible by 7. And if I get a remainder of 0, that means 7 divided into it evenly. And if I get a remainder of anything else, like 1 through 6, then that means 7 is not a proper divisor of this number. All right. And then 47 is the last number to check. 7 doesn't go into 47 evenly. It goes into 42 evenly. But then we're left with a remainder of 5, which you could either express like this or maybe as a fraction like that. Either way, 7 doesn't seem to work. And at this point, with the rest of the primes, I don't really have any cute divisibility rules. And so other primes that we'll just need to check for divisibility are like 11, 13, 17, 19, 23, 29, 31. And I'm hoping that one of these work. So give me a sec to just kind of check the list and figure out which one we're going to land on first. What do you know? It's actually 11. So let's try it out. 11 goes into 265,837 some amount of times. I checked on my calculator and I forget the number already. So let's fly through that long division together. So anyways, my plan is, once I kind of figure out this long division, is to, oops, I just kind of messed up where my subtraction sign goes. I shouldn't talk and do math at the same time. Or maybe I will. Anyways, my plan is to, well, do the long division as I am right now. And then once I find the whole number, which is going to be whatever this is just try the exact same process on it again and again and again, as in keep dividing it by some prime number. Fortunately, I know that all the primes below 11 aren't going to work, because if 5 doesn't divide the big number and I take out an 11, well, 5 isn't going to show up in the smaller number either. So I could do some long division on this slightly smaller number, and I should start out with the 11 again, because it's possible that we have repeated prime factors in the number, and I can't look at this number and know whether or not 11 divides into it. I could maybe look at 99 and see it pretty quickly, but I can't for 24,167. So it's long division again. So let's just kind of run through this again and see what happens. Ooh, that's going to be a 1, right? Yeah, okay. 1, 11. This is kind of interesting, where when I drop it down, there's 3 digits here. That just didn't happen in the other long division ones. No matter. This should be a 9, because then I can subtract out a 99. And then great, I get another number with no remainder. So 11 is a repeated factor. And honestly, it might repeat again. And like I said, some numbers it's easier to spot factors, others there just isn't. And I can't see it in this one. So I'm going to have to try 11 once again. So let's subtract out the 11, drop down the 9. That's going to be another 99. Ooh, there we go. And then this one I don't think is going to work, right? Because then, 109 minus 99 is 10. Drop down the 7. And this isn't a multiple of 11, right? Because 99 is 9 times 11. And then the next one would be 110. And so this tells me that 11 is not yet another factor of this number, and I should try the next prime. And I did check beforehand, 13 does work in this, so I am going to just kind of run through the division here. Oops, that's not where 13 goes. I believe 13 goes into 21 once, and we're just going to blaze through this until we figure out how many times 13 goes in this number. This should be a 6, I think, because we get 60 plus 18, which is 78. So let me put a 6 here. I'll do the subtraction, I guess, after I bring down the 7. 117, it looks like. And, ooh, I can see this as 130 minus 13. And so I know that 13 times 9 is 117. 117 looks so prime to me, but I guess it's a composite number. There we go. And now we can split the 169. This is a square that I've memorized. This is just 13 times 13. So by doing all these divisions, we don't actually have the number of proper divisors yet. We know the prime factorization, which I'll write in 2 seconds. I'll clean up the whiteboard. But we're still not done. We still don't know exactly how many proper divisors there are. So now that we have the prime factorization, we can count the number of proper divisors by kind of thinking of some counting principles, actually. So any number that I pick from any amount of 11s or any amount of 13s, well, up to 2 11s and up to 3 13s, if I multiply them together, will create a divisor of our big number. And so say I pick no 11s and no 13s, then to me that's the number 1. Doing no multiplication would produce the number 1, and 1 is a proper divisor of our big number. And so this is the first proper divisor that I'm going to write in this list. I could also have 1 11 and still no 13s, and that will just be the number 11. And I could have 2 11s and no 13s, and that's going to get me the number 121. And so I could choose 0, 1, or 2 11s to multiply in to create a divisor. And I could choose 0, 1, 2, or 3 13s. And any collection of 11s, up to 2 11s, and any collection of 13s, up to 3 of them, when I multiply that group together, I will create some kind of number that then divides the big one. The one catch to this problem, the proper divisor comes back again, because if I bring all of my 11s and all my 13s to the party, I create the same number again. And that's not a proper divisor, because proper divisors must be smaller. So to count the total number of divisors, I'm just going to do 3 times 4, because I have 3 options for how many 11s I have. I have 4 options for how many 13s I have. And so 12 is the number of divisors. And I just need to take away the number itself to then figure out how many proper divisors I have, which is 11, and that matches today's date. So once we found the prime factorization, we could then do a little bit of counting, and that finds the 11 proper divisors for today. Sweet. I'll see you in the next video.